So I hear the tour is great, so you should do the tour. I'll encourage you to do the tour. All right, so let's see. So one thing from last time, as various people pointed out, and it just worried me for a bit, but it was because my notes had something else, but it's fine. So in the chiral multiplet, in the supersymmetry variations, I should have written that the variation of p left of chi was equal to the expression that I wrote down. So in particular, 1 on root 2 p left gamma m tm z minus m z bar times epsilon. Okay. So I'm going at about half the pace I thought I might go, which is like good. So at some point we'll have a choice, maybe next week, about which things you want to focus on. So I can kind of either tell you more about supersymmetric backgrounds, or I can tell you more about just supergravities in all different dimensions. I'm kind of tempted to tell you about supersymmetric backgrounds, but you can vote on that if you like. And I realize we haven't yet written down a supergravity theory. And I'm still not going to write down a supergravity theory because today I'm going to tell you some geometry, which is going to be geometry that's sort of going to be useful to use in all the rest of the stuff we do. So again, I'm going off on a bit of a tangent, but I hope it's a helpful tangent. And the idea of what I'm going to tell you about is that you may have heard of a whole load of different kinds of geometries. So you know about metric geometries, which are like Riemannian geometries. You might have heard about complex geometries, complex manifolds, or Kähler manifolds, or you might have heard of symplectic manifolds, or Calabi-Yau manifolds, or G2 manifolds, so they're all geometries that have a manifold with some kind of extra information on it, like a metric or something. So what I'm going to do is I'm going to tell you a way of thinking about all those different kinds of spaces in a sort of unified way. And it's useful because those kinds of spaces appear both when you write down the general supergravity theory, they appear not in the geometry that of the space-time, but a general supergravity theory will have some scalar fields in it, and the scalar fields will live on a space, which is one of these special kinds of spaces. And the other way they appear is if I look at a supersymmetric background, then these special spaces appear. So I thought it was useful to give you a way of thinking about all those backgrounds, and then we'll use it in different ways. So that's where I'm going. Does that make sense to people? All right. So what that, and secretly it's my, my pet obsession anyway, so I'm just telling you about the things that I want to tell you about. So I'm going to tell you about G structures, connections, and torsion. So this is basically going to be some differential geometry, things that I think probably many of you already know, but maybe in a slightly different language. So let me start by telling you what a G structure is. And this is going to be the sort of thing that encapsulates all these different kinds of geometries. They're all really just G structures. So why are we doing this? Well, we're going to be considering gravity. So that tells us that we're doing geometry. And we're going to see two kinds of, we'll see special types of geometry. And we'll see them in two different ways. One, we'll see them as what are called supersymmetric backgrounds. These are things that are a sort of configuration of the fields in supergravity that preserve some number of supersymmetries. So in the same way you could have a background that had a killing isometry, right, that was invariant under some translation, you can have a background that's invariant under some supersymmetry transformation. So these are invariant under a supersymmetry transformation. And then the other way we're going to see these things is that general supergravities have scalar fields, include scalar fields, so some phi I with some I index. So in 4 dimensions, we said looked like the supergravity was going to have a metric and this spin 3/2 field. If I'm in higher dimensions or I have more supersymmetries, it might have metric, spin 3/2, spin 1, spin half, and scalars. So in general, I'm going to have scalars. And they'll have a kinetic term so something like this. So I'll have some d mu phi I, sorry, dm phi I, dm phi j. And in general, what you get here is a sigma model. Let me call it something else. Call it capital G, ij. I'll get in the kinetic term, I get something in front of the kinetic term, right? It's not just the standard kinetic term, which depends on the scalar fields. So you can think of these guys as some parameters in some scalar field space. And this thing, Gij, is a metric on M. So it's not a space-time metric, it's a metric on the space of fields. Does that make sense? And again, what you find is that this M gets some special geometry in a supergravity theory. So in general, this is not just a generic metric, but it's a special kind of metric. It could be like a Kähler metric, or it could be something more complicated, okay? So the way in which these geometries are going to appear is, one, as actually space-time geometries that preserve supersymmetry, or two, as things that appear in the kinetic energy term for the scalar fields in the supergravity. Or more generally, if you couple supergravity to some other matter, you also get things like this. Okay, does the motivation make sense? All right, so let me now tell you about G-structures. So what I want is some way of talking about these special kinds of geometries. So let me just start with some, so we start with just differential geometry. So just as some notation, so let's have some manifold. This is some d-dimensional manifold. And then I'll call Tm, that's the tangent bundle. And then I'll write sections of the tangent bundle, so those are vector fields. So that's some vector field that's a function of it. And I could write that in components like this. So I hope everyone is happy with this kind of notation. Is that okay? Ish. I should say that the other way around, shouldn't I? It's always bad to say everyone is happy with. And then there are things which are going to be cotangent. So these are things with an index up. There are things with an index down, which could be lambda m. And there, conventionally, you write it as a dxm. So these are just contravariant and covariant vectors. I think you know this from general relativity, right? Etc. So then we can have other tensors. So something you can do just completely in general, You're used to doing this maybe if you talk about spin connections, if you've got a metric, but I'm not doing that. I'm just doing it completely in general, is that you can define you can always, one can always choose a basis. For T of M at a point X in the manifold. So what do I mean by that? So I write a vector as some VA E hat A. So here I chose a basis that was the coordinate basis. I just used the coordinates. But in general, I could just choose some set of basis vectors, right? Where this set of basis vectors is a basis of the vector space at the point X of the tangent space. Is everyone? Yep. No. So yeah, it has to be complete and not orthonormal. I don't have a metric or anything yet. It just has to be a complete basis. Or frame. Sometimes I'll also call it a frame. So if I have any two frames are related by just some general linear transformation, right? So if I have another basis, just because they're both complete bases, I have to have that this basis is some rotation of this basis, where this is going to be an element of just a general linear transformation. Right? I'm not saying anything very deep. Just choose different bases at different points. Each basis will be related to another one by general linear transformation. Everyone's happy? Okay. So then I can construct something which is called the frame bundle. So if we define at X, if we define f of X to be the set of all frames, or bases at X, then we can define we can define what's called the frame bundle of the manifold, which is going to be, okay, this is, disjoint union, but don't worry, I'm just putting together all the different frames at each point. So what's going on? So if this is my manifold, at each point here, I could have a little frame. Right? And what this frame bundle is all the different choices of frames I could make at every different point. So it's important to remember that because this manifold can have non-trivial topology, there's no sense in which I can choose a frame everywhere continuously on the manifold. If I could do that, the manifold would have something called, it would be called parallelizable. It means I can introduce a global frame everywhere. It would be like it would be like Rn or some quotient of Rn. Okay. So, or it could be more than that, but that would be an example. So generally, the non-trivial topology of M means you can't choose a global frame but can choose frames on patches. So if I have patches on the manifold, right? So in general, if I have two patches on the overlap, so if I have, so I could have a frame E hat A on U, and I could have a frame E prime A on U prime, and on the overlap, the two sets of frames would have to be related by some. Oops, sorry, I'm writing this. How am I writing this? Would have to be related by some GLD transformation. So I'm just saying on one patch I choose a frame, on another patch I choose a frame, and then I have to map from one frame to the other on the overlap. And actually it will be these different maps on the overlap that will tell me about the topology of the manifold. If I'm not making sense or I'm making too much sense or something, stop me. And is this all right? Ask me a question. Say again, sorry. On patches. Sorry, yeah. Yeah. So it's D because it's D-dimensional, and it's R because these are all just real vector spaces. So the most general thing is that I patch with this. Now what can happen is that I could have a manifold where the topology is such I could actually do the patching with a smaller group. And that's actually where we're going. That's going to be what I call a G structure, is something where I can patch the frames together with a smaller group than the full thing. Yeah.
What's the minimal number of patches that you need to describe necessarily?
So it's the same as any, you can just pick up any topology book for like manifold topology, and it's the same story. So I just take the topology of the manifold, some set of open sets, that's enough. Because I haven't put anything new in here, right? All I'm doing is just this differentiable manifold. That's the only thing that's gone in. I've just said, here's a way of constructing something on it. I haven't done anything more. Yep. Yes? Yeah, so you could think of f of x as a vector space where the elements of the, actually going to think of it more like a group. So like any 2 points in f of x are related by a group transformation. So locally, f of x actually just looks like the group GLD. Yep. Yep. Yeah. Yep. Yeah.
So this setup can be applied to any spacetime metric as well. It might not be because.
Yeah, so I haven't, no, excellent. So this is just the topology of the manifold, just the differentiable manifold. I haven't even put a metric on it yet.
No, you wrote down the derivatives as just d mu.
Yeah, so no, but at the moment, so there's no metric. It could be Minkowski space. It could be any space you want. Yeah, good. Any others? Yeah. You can, yes. Yep. So let me tell you what this structure gives you. So this structure gives you what? So geometrically, this frame bundle is what's called a principal bundle principal bundle. Or I guess I should say a principal G bundle with G is GL dr. So what does that mean? That means that's equal to a bundle where roughly the fibers are Lie groups, G. So if I pick one frame, let me fix one frame at the point X, every other frame I can get to by GLD transformation. So if I thought of that first frame as the identity, I can get to every other one by the action of an element of GLD. So that makes the fiber look like the group. Okay? So you can think of this as a bundle over the manifold where instead of having a vector space on each point, you have a group on each point. Does that make sense? And indeed here you say that G is the structure group of the manifold. So it's exactly the thing that you have to patch by in order to describe the patch with to describe the topology. So let me tell you where I'm going. I'm going to try and introduce things that are the analogs of metrics in each case. And you know that when you do general relativity, there's a very particular connection. That's the key connection you do, which is, okay, the Italians should pronounce it for me. I would say Levi-Civita. Am I okay? Okay. And that has two properties, right? The derivative of the metric is 0, and it has no torsion. So what I would like to do is to think about the analog of the Levi-Civita connection on other kinds of structures I could put on a manifold. That's where I'm going. Okay. So what's a G structure? So the definition is that it's a it's a principal subbundle P of the frame bundle with group G, which is a subgroup of GLDR. So how should you think about that? So that means, so at each point, P of X, which is a sub-bundle of the frame bundle at X, picks out a subset of frames. Right? At each point it's a subset of frames, and they're related by the action of G, which is a subgroup of GLDR. So what I mean is that if E hat A and E hat A prime are elements of P of X, then E hat A is equal to M A B E hat B prime, where now M has to be an element of G. Right? So you're actually really familiar with this, I think. So let me give you an example. So if I have an OD structure, this is the same as having a metric. So why is that? So I can define P of X to be the set of orthonormal frames. Right, so that means I take a frame and I require that when I contract the frame with the metric, they're orthonormal. So that's what you're used to doing in general relativity if you want to start talking about spin connections or something, right? Have people seen spin connections on? No, okay. So that tells me that if I have a metric, and if you think about the rotations here, right? So if I have some prime, which is some M, A, B, E hat B, then I'm going to need, when I act in here, I'm going to have G, M, N, E hat prime, M, A, E hat prime, N, B. And that's going to be, how are we doing? That's going to be A prime, B prime, G, M, N, E hat M, A prime, E hat N, B prime. But this is just M, A prime, M, B prime, delta A prime, B prime. And I'm going to require that to be delta AB. But that just tells me that M has to rotate in the orthogonal group. Right? This is just MN transpose. So if I take any two orthonormal frames, they're going to be related by an orthogonal transformation. So indeed, they're going to live in, the structure group is going to be OD rather than GLD. Yeah.
What are the conditions on the manifold to be able to define first the GLD bundle and then an orthogonal?
Excellent. So did anyone ever tell you that there are manifolds you can't put metrics on? I think not, right? Everyone always says you can put a metric on any manifold. And that's true. And the reason it's true is that if you have a group and you're patching the manifold with the group, the non-trivial topology in the group is all contained in the compact part of the group. So OD is the maximally compact subgroup of GLD, and any non-trivial topology in GLD is contained in the maximally compact subgroup. So because I'm taking the maximally compact subgroup, there's no extra topology I can put in by doing GLD patching. So that means that's why every manifold admits a metric. Yeah.
One way of doing it is where you have a metric, you can go that way.
Yes.
Going that way is less obvious to me.
Yes.
I feel like you need to make a choice of like, what do you need to go
Yep.
Take some frame, act on it with OD, and it's going to rotate it around.
Yep. So let's try and do it the other way. So yeah, absolutely. This was the one that said that from the metric, I got the P structure. So let's go the other way. Suppose I've got P, how do I go to the metric? So for P, this means I've got some basis of objects some set of frames. So usefully, I can always define the dual basis, right? So this is a basis of things that live in the cotangent space. So these are things with down indices. And I define them just by saying that E, A, M, E hat, A, N is, sorry, got it exactly the wrong way around. B, M is delta AB. So when I take the basis in the vector space, this is the dual basis in the cotangent space. So these are two dual vector spaces. So if I have a basis in T of M, I get a dual basis in the dual space just by saying that the basis vectors, when I contract them as zero, give me a delta. Does that make sense? I've got a vector, I've got an index up and an index down, so I can always make a contraction. If I have these guys, I can find a set of these guys that satisfy that. Yeah. So there's two different things. On a vector space, I could have an inner product on a vector space. I can also always, I also have the dual vector space. If I have a basis on here, I always get a basis on here without needing any metric or anything. If I want to associate this basis to that one, then I need a metric to go from one to the other. Yep. So from this, I can then define a metric GMN, should just to be delta AB, EAM, EBN. So that means if I take a given basis here and then I go through this procedure, I now get a metric. And if I chose a different basis, if I chose E hat prime A, should be M A B E hat B, then I would have E prime A would be M inverse B A E prime B, just from the way this is defined. And this thing, G prime MN, would be M inverse A prime A, M inverse B prime B delta A prime B prime E A M E B N, but this whole thing is just delta AB because these are orthogonal transformations. So if I choose a different basis, I get the same metric. So each basis I choose in here will define the same metric. I don't know if it's because it's like 9:30 and it's a long week and everyone's tired, or if I'm saying things and it's not making sense. If it's not making sense, make sure you ask me questions. Okay? So what I'm saying is a metric is equivalent to a set of orthonormal frames. And they could be orthonormal frames defined, yeah. They can be orthonormal frames as a basis for vectors or as a basis of one forms, of contravariant or covariant vectors. This basis is sometimes called a Vierbein basis, or a frame, or a Vielbein, or if I'm in 11 dimensions, like a Zweibein, or like, okay, so there's, no, Zweibein's 2 dimensions, yeah. Okay. But does the basic idea make sense? Yeah.
Just to make sure my science
Good.
is having a G structure somehow a weaker condition than having a G bundle? Or
So a G structure is a G bundle. Where it's a principal bundle, so each fiber is a group G. But the G bundle has to be a sub-bundle of the frame bundle. Yeah.
so in that sense, is it a stronger condition or a weaker condition?
It's a stronger condition because you have to be able to pick out this subset of frames. So in general, you won't be able to do that because the way the frames patch, they'll force you outside the subset you're trying to choose, right? So in general, picking a G structure is a it constrains the topology of the space. Yeah. Yeah.
Allow me to check if I understood it correctly. So the constraint that you have written down inside the curly braces in the top code, yes. So that basically means, I think that is the only case where the information from OD comes in. So it means one basis vector when parallel transport is along the manifold of fields corresponds to the same vector in another point of the manifold of the fields, but it cannot be parallel transported to any other basis vector.
Yes. So that's one way to think about it, where I introduced a connection and I started thinking about parallel transport. That's certainly absolutely true. So, but all I really need is the metric at each point, and I make sure that I choose at each point in the manifold, I choose a frame so that it's orthonormal with respect to that metric, so that it satisfies this condition. Yeah, and then I just do it smoothly so that the frame smoothly changes as I go. Yeah. Yeah. No. Yeah. Yeah, so literally as a tensor, the two metrics are the same. They're not really two different metrics. I'm just saying that each frame defines the same metric. So if I choose, no, this is excellent. So like, what I'm trying to say is if I fix my metric, every frame I choose here will define that same metric. If I choose a different metric, I'm really choosing a different subset of frames. So changing the metric changes the G structure. It picks out a different subset of frames. Does that make sense? Yeah. Yeah. Yeah, so once I fix the metric, each field biome will be related by a Lorentz transformation. Yeah, and that's here I'm doing it, instead of doing Lorentz, I'm doing OD, but I could equally have done O d minus 1, 1 if I wanted, and then it would be Lorentz transformations. Yeah, thank you. But if I choose a different metric, then I'll get a different set of frames.
Okay, but then those will again be related to each other.
They'll be related to each other by a GLD transformation, but they won't be related by a Lorentz transformation. Yeah, exactly. Yeah, exactly. So when I say this subbundle, there's more information here. There's the group, but there's also exactly what subbundle it is. I could be different subbundles, right? I could choose the subgroup in different ways. And when I do that, that changes what my metric is. All right, so that's one you're kind of familiar-ish with, which is Riemannian geometry. So let's do another example. Yep. Mm-hmm. And the way everything patches together. Is that what you saw? And A subbundle and? Yes, so by saying it's a subbundle, it has to be a principal bundle, so it will have a group G that relates, so the fiber looks like the group G of the.
When we say a dish factor, you're specifying use
And the way that group embeds inside the principal bundle, yeah. All right, so let's do another example. So I'm going to do, let's do an SLDR structure. And this is going to be equivalent to an orientation. I'll call it kappa. So this is a much weaker thing, right? This is a much bigger group inside GLDR. And somehow all I'm doing is fixing that my matrices now that relate different frames, instead of being GLD matrices, have to be SLD matrices. So what's this equivalent to? Well, it's an equivalent to something which is a volume form. So this is something with M1 through MD indices. So it's like a top form. Are people happy with differential forms, P forms? Things with anti-symmetrized indices, down and stairs indices. And how do I construct this from the frame? So this thing is equal to, and then conventionally I'll put a 1 on d factorial, and then I'll take my dual frame, and I'll contract it with an epsilon tensor. So this is just the thing that's antisymmetric, totally antisymmetric in D indices. Yep.
Why you wrote G inside the
Thank you. So again, I'm using the dual frame here, right? Because I want something with down indices instead of up indices. But if I think about doing transformations on these things, I'll transform by a GLD transformation, but it has to preserve this thing, which just takes the determinant of that GLD transformation. So this thing will be invariant. This is invariant if and only if the determinant of M is equal to 1. Precisely because this epsilon tensor just takes the determinant. Does that make sense? And this says that it's an orientable manifold. So it means that if I have a frame, I can put an orientation by ordering the frame. That's what this does. It orders these things in a particular order. And then what it says is I can keep that ordering everywhere on the manifold. So as an example where you can't do that is a Mobius strip. So you'd start with an ordering one way, you go around the strip, and it wants to come back to ordering the other way around. It's like flips, it has a minus sign in it. So this doesn't allow any like reflections as you go around. Yeah. Yeah. Good. So let's think about, if we thought about the Mobius strip. So what does that look like? I'm not going to draw it very well. It looks like a strip where you match that direction with that direction as you patch it together. So let's start here, and let me choose a little orientation like that, which is E1, E2. And then I take this across here, and I'll still have E1, E2. But now I make the map, and when I map it back to here, it's going to look like E1, E2. And there's no way I can rotate that one, right? That is different from that orientation. Because this orientation, when I go from 1 to 2, I go around that way. So put another way, here, let me do it better. Let me do the dual basis. So here, kappa is E1, I'll write wedge E2. That's what that thing does. It does a wedge product. When I go around here, it's gonna, when I map around, I get a kappa prime, which is gonna look like, it flips E1, so it's gonna look like minus E1 wedge E2. But minus E1 wedge E2 is not the same as E1 and E2. So I can't choose a kappa everywhere on here. The topology doesn't allow it because it gives me this extra sign when I go from one to the other. Yeah. Yeah. So this transformation here, when I go around, is something that's in GL2 but not in SL2. It's a reflection. It's something which looks like 1 minus 1. Or minus 1, 1. So it's, yeah, good. Are there other questions? Yeah. You can, yeah, so you can. So the frame is defined so that when I contract with kappa, I get this antisymmetric thing. And then the kappa is defined by going to the dual frame and writing this thing. So it's the same idea, yeah. Okay. So now I'm going to do, when do you want to stop? Do you want to stop now? Do you want to stop now for 5 minutes and then we'll come back? Yeah, go on.
Sorry, why is it not sufficient to just have data greater than 0?
Sorry, say that again.
Why is it not sufficient?
So let me tell you what that's equivalent to. So in each of these cases, we saw that the structure was equivalent to some tensor. So the same thing happens here. So P is equivalent to a tensor, which I'll call I, which has one up index and one down index. And this tensor I is going to play the role of I squaring to minus 1. We now have complex numbers. So this has the property that IMP IPN is equal to minus delta MN. Okay. And this I is actually defining this subgroup in here. So let's I defines a GLNC subgroup, and let's see how this works. So how? So let's suppose I just define I. So it looks something like 0, 1, minus 1, 0, 0, 1, minus 1, 0, 0, 1, minus 1, 0. Okay, so I'm just working at a point. And I have my vector, which is V1, V2, V3, all the way down to D2n. So if I act I on V, what happens is that V1, so if I call V prime this action, you notice that V prime 1 is just going to be equal to V2. V prime 2 is going to equal minus V1. Actually, maybe this is exactly how I don't want to do it. let me put some signs in here. It's going to be minus V2. This is plus V1. V prime 3 is going to be minus V4. V prime 4 is going to be V3, etc. Right? But this is the same as saying V prime 1 plus I V prime 2 is equal to I times V1 plus I V2. Right? Because now V prime, did I have it the right way? Yeah, so now V prime 1 is minus V2, V prime 2 is V1, and so on, right? So this is allowing me to pair these things together into a complex combination. And when I pair it, you notice that this matrix acts like an I. So in fact, the group, if I require that M inverse is equal to I, then M is an element of GL and C. So the subgroup of matrices that preserve this I matrix are exactly the ones that live in the general linear complex group. Is that okay? Yep. Okay, so it's not a complex structure because it doesn't yet allow me to introduce complex coordinates. All it's done is said that the frame reduces. And what's going to happen is we have to put some differential conditions on this structure in order to say you can introduce complex coordinates. Yep. Yeah.
You have like GLN-C as a subset of GL2NR.
Yep.
One has real entries, one has complex entries.
Yeah.
Is it like isomorphic to some real, like subgroup of real entries?
Yes, so the way I'm doing this group here has real entries, but it's isomorphic to the group GLNC. And this is kind of the isomorphism, right? I'm just thinking of a complex number as two real numbers. That's exactly the way it's working, yep. So it's like the isomorphism we did between quaternions and complex matrices, yeah. Okay. So if you like, what's going on here is that so in terms of frames, we can introduce a set of frames that look like V1, F1 looks like E1 plus IE2, F2 looks like E3 plus IE4, all the way up to Fn, which looks like E2n minus 1 plus IE2n. So this is sort of a set of complex frames. And these are related by a GL and C transformation. Okay, and you see it's sort of it's a subset of the possible relations you could have because I have to keep them paired up. Yeah.
So if you would think about this in terms of real matrices, you could say that it's actually like E1 is an identity matrix and like E2.
Yeah, so I could use this matrix to say, for example, that I acting on E hat 2 has to be E hat 1, and I acting on E hat 1 has to be minus E hat 2. Sorry, that's exactly the wrong way around. I2 is minus E1, and that's by 2. Because this I is like multiplying by I. So if I multiply by I get I and this, so that's going to be the, yeah. Okay. So another way of saying this is that the complexified tangent space decomposes into plus or minus I eigenspaces under I. So I can take, when I put a C here, it just means that I allow myself the vectors to be complex objects rather than real objects. And it decomposes into 2 bits, which are usually called 1, 0, plus 0, 1. And these are the ones that have the plus I eigenvalue under the action of I. And these are the ones that have the minus I eigenvalue under the action of I. So these will have a basis that looks like F hat I. And these will have a basis that look like F hat star I. So these will have a basis that look like E1 plus IE2. These will have a basis that look like E1 minus IE2. Did I lose you, or are you okay? Yeah. Okay. Good. So the basic point is that if we don't worry too much about the frames, so believe me that a choice of frames is equivalent to some object. The object here is going to be some tensor Mn that satisfies this property. And that's all I need. That's the analog of the metric, is this thing. And my claim is, if I have that thing, I can define a set of frames which are now rotated into each other under GLNC. Okay. Given that set of frames, there's a natural kind of complex set of frames complex frame you can choose, which is these ones. So suppose I have a set of frames which are compatible with this I thing, right? Then I can define this complex set of frames, and and that allows me to decompose the tangent space into a kind of complex bit and a complex star bit by taking the basis of these frames and a basis with the complex conjugates of those. So all I'm doing is taking, if you have I'm just saying the overall basis is going to have, 2n things. I can group them this way with plus i's and then another set with minus i's. It's still a 2n dimensional basis. And I can think of them as one set having a plus eigenvalue under this action of I, and the other having a minus eigenvalue under the action of I. Yeah.
The composition with respect to plus minus I eigenvalues.
Yeah. Exactly. So if I was actually in a complex manifold, these would be the holomorphic vectors, and these would be the anti-holomorphic vectors. If I really had complex coordinates, but I don't have complex coordinates yet. Yeah. 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 Yeah, so because I'm embedding everything in the real thing, I kind of have that map built in because I'm embedding it already in the real group. Yeah, but that's exactly right.
Whether it's D01 thing, right? Minus I, and then it's up on the downstairs.
Oh, so this is Fi, so this is this basis. This is the complex conjugate basis. So I take a star, and sometimes they're labeled with a kind of barred index, I bar, but yeah. All right, so let me do. Let me do another example. So let me do what's called an almost symplectic structure. So that's going to be some symplectic group inside GL2NR. So what's a symplectic group? Well, now I need an object Mn, which is a 2 form. So that means it's got Mn is equal to minus Nm. So it's a bit like a metric, but it's anti-symmetric instead of symmetric. And I also need that if I take the wedge product of this thing n times, this must be non-zero. So this just says it's non-degenerate. So I'm using wedge products. Is that okay for differential forms? If that's not clear, what I mean by this is if I take M1, M2, M3, M4, all the way up to M2n minus 1, M2n, and anti-symmetrize on everything, that has to be non-zero. Yeah. That should be T star. Yeah. Any other questions? So actually, I can again write this thing in this sort of off-diagonal form. But remember now, this is something with 2 down indices, not with 1 down index, 1 up index. And the symplectic group is defined so that if I have M omega M transpose, this has to be omega. This gets the transpose here, right, because they're both down indices rather than the inverse, because one was up, one was down. So this thing defines the symplectic group 2NR inside GL 2NR. So again, it's not yet a symplectic manifold because it's going to have to satisfy some differential conditions, but it's heading towards symplectic manifolds, and symplectic manifolds are like the geometry of classical mechanics, right? If you have momenta and position and momenta, that's the geometry that goes into classical mechanics. Okay, and let me just do one more example. So again, there's a corresponding frame you can write down, but I'm just not bothering to tell you what it is. Well, or maybe I could say so that you can fix a frame, fix frames, such that this guy looks like E1 wedge E2 plus E3 wedge E4 plus all the way up to E2n minus 1 wedge E2n, where these are the dual frames. And this wedge just means anti-symmetrize on the indices. Sorry, the way I'm doing this should be up 2, 2, 3, 4, 2n minus 1, 2n. Okay. Let me just do one more example. That's a trivial structure. So G is just the identity. What that means is that I have a global frame. Right? I don't have to do any patching at all. It means I have a global frame. I can define D vector fields continuously, non-zero D vector fields smoothly on the whole manifold. That's the same as what's called parallelizable. Parallelizable. So the two-sphere, for example, is not parallelizable. The two-sphere, you can't even define a single global nowhere vanishing vector field, right? That's the hairy-ball theorem. It always has to vanish somewhere. You get a little. The three-sphere is parallelizable because the three-sphere is the same as the group SU2. And on the group SU2, you can introduce left invariant vector fields, and they're globally defined. So each of these things puts a topological constraint on the manifold. Parallelizable is very strong. Admitting an almost symplectic structure is not all manifolds admit that. Admitting an almost complex structure, not all manifolds admit that. All right, so in general, a G structure, so not all manifolds, well, let me note that a G structure restricts the topology of M. What I mean is only certain topologies of M will admit a given G structure. And typically, a G structure is equivalent to maybe a set of invariant tensors. So for example, if we have OD, that corresponds to a metric. If we have GL and C, that corresponded to this almost complex structure. If we had the symplectic group, that corresponded to this two-form, etc. And let me just say, for example, if you had a UN structure, well, if I have GL2NR, I can have a symplectic group that's got an omega. I can have a complex group that has an I, and the common subgroup of these two things is a unitary group. So that's equivalent to specifying two things, this almost complex symplectic structure and this almost complex structure. So a UN structure is equivalent to having both things, omega and I. Yeah.
I can see how they're having specifying a bunch of tensors. I'm not quite sure what invariant tensors.
So what I mean is that these tensors are invariant under G. Yep. The point was, yeah, whichever frame we chose, you got the same tensor. Yep. Any other questions? Okay, so lots of setup. So now we want to get the payoff, which is I want to talk a bit about connections. and torsion. So the idea is when do we have the analog of the Levi-Civita connection for a G structure? So Levi-Civita, right, is a connection that has the property that the derivative of the metric vanishes and it has zero torsion. So a very natural thing to ask is, suppose I have an almost complex structure and I choose a connection where the derivative of the almost complex structure vanishes and it has no torsion. Can I do that? What happens when I do that? What about this one? What about this one? Okay. And when you do that, requiring there to be such a derivative puts in, for a metric, you can always find a Levi-Civita connection. For these other things, you can't always find a corresponding torsion-free connection. It's only if the structure satisfies certain differential conditions that you can find it. And that's what a complex manifold is. A complex manifold is one that admits an almost complex structure, and that almost complex structure admits a torsion-free, a connection with no torsion. And that's what a symplectic manifold is. It's one that has a symplectic structure, and you can find a connection. The derivative of the symplectic structure is zero, and it has no torsion. Yeah. Also, yes, so again, it means that not all manifolds that admit a almost complex structure will be actually admit a complex structure, because you have to satisfy these extra differential conditions. And the reason I'm going through all this is that all the special geometries that you see when you do supergravity or supergravity backgrounds are of this type. So Kähler manifolds, Calabi-Yau manifolds, they're all of this type. Okay. So let's talk a little bit about connections. So a connection, if you remember, so you can define it just in general, right? So it's something which takes vectors and maps them into something that have a downstairs index and an upstairs index, right? So if I have Vm, it maps into something with like that, right? It allows me to take derivatives. Yep.
In a physical theory, is there a process to get those Imn or omega mn? Like the way we get Gmn from the Einstein equation?
Oh, yes, so you can also write down dynamical theories of a given structure. So Riemannian geometry is like a dynamical theory of a metric. You can ask, can you start writing down dynamical theories of complex structures, or like, and actually these things appear in the topological string. So topological strings you can think of as being a dynamical theory of complex structures or a dynamical theory of symplectic structures in some sense. It's not as simple as writing down a curvature and so on, but it's got the same idea, yeah.
They would arise from an action?
So there can be an action that you can write down, which is like the analog of the Einstein-Hilbert action, but for complex structures or symplectic structures. Yep. Yep. Oh, sorry, sensor TM. That would be better, wouldn't it? Yep. So you're used to thinking about this in coordinates, right? And this I could write it as some dnvm plus, and I'm not doing anything metric here or anything, so it's not the Christoffel connection or anything like that. So let me just write it as an omega nmp vp. This is just some bit that does the inhomogeneous, transforms inhomogeneously. But I could actually do this in any basis. So this is kind of in the coordinate basis. Where I think of Vm, so I think of V as Vm d by dxm. So, I mean, people say different things. For me, I will think of nabla as the connection. Yeah, yeah. But I could also write this in a general frame. So I could think of V as VA E hat A. And then I'd write nabla M VA would look like dm VA plus something. How did I write this actually? Sorry, let me change notation. Okay, so this, I will write this like the way you usually write, as though it was a Christoffel symbol. But just remember, it's not a Christoffel symbol yet, right? It's just some object that transforms inhomogeneously. So I could always write this, and it will again be some object that appears here. Let me call it big omega.
I suppose the gap in the downstairs indices is not correctly the Christoffel symbol because.
Sorry.
I suppose the gap in the downstairs indices of Christoffel symbol is not correct because it doesn't.
Yeah, you can't. If you lowered this, I mean, I don't even have a metric, but if I lowered this index from the metric, I have to distinguish these indices. So I'll put a little gap there just because it reminds me that yeah. So I could have written the same thing in a general frame, and these two things, this is related to this guy, right? It's just by a change of frame. It's going to be an inhomogeneous change of frame because I've got this derivative here, right? So it's going to depend on derivatives of the frame in some sense. But these two things are related to each other. So from a mathematical point of view, this gamma is just the connection. Sorry, I'm now calling gamma the connection, but you know what I mean. In the coordinate frame. So all I'm trying to say is I can think of my connection in coordinate frame or in some general frame. I can do either one. I have a way of going from one to the other just by using the frame. It gives me a complicated relation between the two of them, but I can always write it down if I want to. Okay. All right, so and I can also act, so of course I can act on a general tensor with nabla. So for example, if I did nabla m of t, a, b, c, this would look like the derivative of t, a, b, c plus omega m, a, d, t, d, b, c plus omega m, b, d, t, a, d, c. And then when it's a lowered index, I get a minus sign, omega m, dc, t, a, b, d. Right? So it just extends to taking derivatives on any object. And then there's another thing you can define. You can always define the notion of torsion. So we can think of torsion as an object which is a section of Tm tensor wedge 2 T star M. And in coordinates, we define the torsion, so TP Mn with two vectors Mn, Un is just Vp nabla P acting on, oops, sorry. Yep.
The definition of the connection in the frame, the index M is a coordinate index.
Yeah, just,
Generally, you can also have another index that.
I could replace it with a frame index by putting a suitable frame in front of here. By putting an EMC there, then yeah, it could become a frame index. Yeah, good. So the torsion is defined in the following way. So I take Q, derivative along Q of UP minus UQ, derivative along Q of VP, minus the Lie bracket between V and U. So if you remember, the Lie bracket is something that looks like VQ. So this thing is VQ dQ UP minus UQ dQ VP. And this thing is a tensor, so for all U and V. So in particular, this thing becomes equal to, in the coordinate basis, it just becomes Mn minus Pnn. So I can define it in general. In the coordinate basis, it just becomes this thing. Okay. So then we say if a G structure P is defined by a set of tensors, let me call them chi I. So these are just some tensors, there might be more than one of them. Then a connection is compatible if the derivative of each of these things is 0. So I'm dropping all the space-time indices, right? This is just some general tensor. So for example, OD compatible means that the derivative of the metric is 0. If I had SP2NR compatible, then the derivative of omega MP would have to be 0, and so on. So this is, I'm working towards the analog of Levi-Civita. I need something where the derivatives of the things that define the structure are 0. More abstractly, if I had a frame, is a frame for P, then I need that the derivative of this thing is minus some omega B, omega BA E hat B, and I need that this thing lives in the adjoint, or it lives in the Lie algebra. It's in the Lie algebra of G. So what that's saying is when I take the derivative, it just acts in a way that keeps me in the same G structure. That's a more formal way of saying what I said above. So now you have a very natural question. So, yep. Sorry, say again. Oh, abstractly. No wonder you cannot read that. Yeah. So you have a natural question. So given P, can you find a torsion-free, that means T equals 0, compatible connection nabla? And if P admits such a connection, then it is a torsion-free structure, or sometimes it's called an integrable structure. So this word integrable is more of a sort of physics way of saying it. A mathematician would call it a torsion-free structure. So the example is a metric, is an OD structure. And the answer is yes. And this thing is unique. And it's just Levi-Civita. So if you ask the same question for a general P structure, you find that so more generally, P has to satisfy a differential condition for nabla to exist. And secondly, nabla may not be unique. And it's the geometries that satisfy this first condition, which are what we call complex geometries or symplectic geometries or whatever they are. So the notion of a symplectic geometry is one that admits a symplectic structure and it actually admits a torsion-free symplectic structure. You can find the analog of Levi-Civita for it. Okay, so I'm sorry that's such a long story, but if you want to think about any of these geometries, G2, Calabi-Yau, hyperkähler, quaternionic Kähler, they're all described in this language. So rather than having to each case tell you what the details are, I just say it's a certain structure that's torsion-free. Okay? All right, so I guess we should stop there. Okay, thank you.